Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 20, Organic Chemistry 3. This is an English version. Today we will continue on terpenes and terpenoids. In the previous lecture, we were talking about the general methods for determination of structure of terpenoids. We have covered analytical methods or spectroscopic method. UV, IR, mass spec, and NMR. Today we will talk about identification of functional groups by chemical methods. Nature of oxygen. The terpenoids generally contain hydroxyl, aldehyde, keto, or carboxylic groups, as well as peroxides. The hydroxyl group can be detected by the formation of crystalline acetate. The organic molecule contains OH. Upon treatment with acetic anhydride or acetyl chloride will give the ester. If the OH is alcoholic, the presence of alcoholic OH can ascertain by dehydration with sulfuric or phosphorus pentoxide. If the OH is phenolic, this type of terpenoids is soluble on sodium hydroxide and reprecipitated by carbon dioxide. It also gives coloration with ferric chloride. If terpenoid forms crystalline addition products like phosphonate derivative, oxime, and phenylhydrazone, this shows that terpenoid contains a carbonyl group. So if we have here carbonyl with sodium hydrogen sulfide will form sulfonate. Carbonyl group with hydroxylamine gives oxime. Again, the carbonyl function with phenylhydrazine gives phenylhydrazone derivative. Aldehydes can be oxidized to carboxylic acids. Aldehyde C double bond OH can be oxidized by chromic potassium dichromate or potassium permanganate to carboxylic group. Ketones are not oxidized under these conditions as they lack the critical hydrogen for the elimination to occur. While ketones are generally oxidized under vigorous conditions, strong oxidizing agent, and at elevated temperature. The oxidation of ketones involves carbon-carbon bond cleavage, resulting in a mixture of carboxylic acids having lesser number of carbon atoms than the parent ketone. Here we have ketone. Upon treated with potassium dichromate or permanganate, concentrated, and here we need heat, will break up to two carboxylic group. This will be carboxylic group and this will be carboxylic group. As an example, we have camphor here. The camphor upon oxidation with nitric as strong oxidizing agent. Again, we break in here. This is carboxyl carbon and this is carboxyl group carbon. If terpenoids having CH2CO group exhibit special properties, this type of terpenoids forms oxime with nitrous acid and benzylidene derivatives with aromatic aldehyde like benzaldehyde in the presence of alkali. So this function CH2C double bond O with nitrous acid and amyl alcohol will form the oxime on the alpha hydrogen. The same carbon, the alpha hydrogens here, with benzaldehyde in the presence of base, they will form C double bond C. Okay, and react with this carbon. Well, the mechanism for this compound CH2C double bond O in a tautomeric form with the enolate. The enolate will react with NO plus coming out of nitrous acid. So protonation in here will form with this protonated species. Elimination of water will give this NO plus. So upon reaction with this will form N-nitroso, which again tautomerize to oxime. We can draw it this way. Intra or inter-hydrogen transfer. Here the same functional group, but in base will be enolate instead of enol. The enolate in resonance with carbon carrying negative charge, which attack like a nucleophile on the aldehyde function, followed by hydrogen transfer and elimination of water to form the benzylidene derivative. Chemical methods for the determination of the nature of unsaturation. Recall that the number of unsaturation from the molecular formula will be the number of tetravalent element plus 1 minus half the number of monovalent elements minus the number of trivalent elements. And 1 degree of unsaturation is equivalent to 1 ring or 1 double bond, 1 bibond. 2 degree of unsaturation is equivalent to 2 double bond, 1 ring, 1 double bond, and 2 rings or 1 triple bond. That's from the molecular formula. The presence and number of multiple bonds in terpenoids have been ascertained by the formation of addition product with various reagents like hydrogens, bromine halogens, halogen acid like HCl, or nitrosyl chloride Tilden's reagent. Well, if we have double bond reacted with hydrogen in presence of palladium and carbon, will give the addition of 2 hydrogen atoms. Bromine will add Br. HCl will add H and Cl on a double bond, and NOCl will be NOCl. Nitrosyl chloride appears as a yellow to yellowish red gas, liquefies at minus 5.5 degrees Celsius. The addition of NOCl gives an idea about the nature of carbon atoms having double bond in terpenoids. So if we have here tertiary in sense of there is no hydrogen on this carbon, addition of nitrosyl chloride will give a blue product. In case of carrying one of these carbon hydrogens, then it will lead to the formation of colorless product. First addition of NOCl, then followed by tautomerization to form oxime, so that will be a colorless product. Predict the number of rings present in the terpenoid having molecular formula. We have here C10H16 and containing one double bond, which means it consumed one molecule of hydrogen to give alkane. Well, from the molecular formula, applying here 10 carbon plus 1 half 16, there is no trivalent, will end up with 3 unsaturation number. Well, it contains one double bond, so it has to be one double bond and 2 rings, like the one we have in here. Alpha bynene. Alpha bynene has one double bond and it contains 2 rings. That's bicyclic monoterpene. Let's solve another one. A terpene with molecular formula C15H24 absorbs 3 molecules of hydrogen to form a saturated hydrocarbons C15H30. How many double bonds and rings are present in the terpene? Well, from the unsaturation and molecular formula rule, we get unsaturation 4. We have 3 double bond because it consumed 3 molecules of hydrogens. Well, then the left will be 1, so we have 3 double bond and 1 ring. Oxidative degradation method. As we know that most of terpenoids are olefinic in nature, and this method may be used to cleave the molecule into simple fragments of known structure and help identifying the location of the double bond or double bonds if we have more than one. Well, oxidative cleavage using hot concentrated potassium permanganate. In potassium permanganate, oxidation will occur first by dehydroxylation, addition of OHs on the double bond. If the solution is warm or acidic or too concentrated, oxidative cleavage of the glycol may occur. So it's further oxidation. In effect, the double bond is cleaved into 2 carbonyl groups. The product may be initially ketones and aldehydes, but aldehydes are oxidized to carboxylic acids under the strong oxidizing conditions. If the molecule contains terminal alkene, so if the molecule has CH2, terminal CH2, the group is oxidized all the way to carbon dioxide and water. You can go and listen to the lecture on that with detailed mechanism. So if you have double bond and these 2 carbons have no hydrogens, well, with potassium permanganate, warm and concentrated, we add 2 OHs on the double bond, further cleave, and this will be carbonyl and this will be carbonyl. There is no hydrogen in here, so ketone and ketone. If one of these carbon contain hydrogens, one hydrogen, well, then we add OH, cleave, carbonyl ketone has no hydrogen. When we have one hydrogen, which means we have aldehyde, it will go further to carboxylic acid. If this car, one of them has two hydrogens, then we get ketone and formaldehyde, and the formaldehyde will further oxidize to formic acid and then further oxidize to carbon dioxide and water. As an example, limonene contains two double bonds. Well, this one has no hydrogen, this carbon, and this carbon has one hydrogen. Here has no hydrogens, and here has two hydrogens. So we cleave in here. This will be double bond O, ketone, and this one will be carboxylic acid. Here will be ketone, and he will be formic acid, which further oxidize to carbon dioxide and water. In here, we have one double bond. This carbon has no hydrogen, and this one has one hydrogen. So this one will be carboxyl, and this one will be ketone. Ozonolysis is another oxidative cleavage process. So ozone O3 cleaves double bonds to give ketones and aldehyde. So if we have double bond, treat the compound with ozone. Second step, using reducing agent like dimethyl sulfide. So we cut in here, we add oxygen up and oxygen down. So we have these molecules. And dimethyl sulfide will be dimethyl sulfoxide. Recall the mechanism. 3+2 addition of ozone with alkene to form monozonoid, which break apart to two species, reunion to form ozonoid. The ozonoid, upon treated with mild reducing agent like dimethyl sulfide or zinc with water, we get the fragments, two carbonyl compounds and dimethyl sulfoxide or zinc oxide if you are using this reagent, zinc water. Let's see what will happen to limonene when we treat it with ozone and then zinc water as a second step. Well, we break in here. This will be carbonyl carbon. This will be aldehydic. Again, this one will be carbonyl, and this carbon will be formaldehyde. So we have formaldehyde, and we get the rest of the molecule intact, 3-methyl, 3-acetyl, 6-oxo-heptanal. Nitric acid. In a few cases, nitric acid is also used to affect oxidative degradation. Nitric is a strong, powerful oxidizing agent. It degrades the terpenoids drastically to a mixture of aliphatic and aromatic acids. So camphor here nitric will break this bond, giving here carboxylic group and here another carboxylic group. A terpene has molecular formula C10H16O, compound A, and it is a major constituent of lemongrass oil. Compound A, on treatment with acidified potassium permanganate solution, produces acetone, oxalic acid, and levulinic acid. Also, compound A gives silver mirror test with tolling reagent. What is the structure of compound A? Compound A, potassium permanganate, acetone, oxalic, levulinic acid mixture. With tolling reagent, it gives positive test, silver mirror deposition. Okay. Well, thinking backward, each C double bond O will get together to form alkene. So in this case, C double bond O, and will be carbon double bond carbon. C double bond O, C double bond O will get together to form double bond. This carbon should carry hydrogen, and this one too, hydrogen, and this carboxylic group would be an aldehyde, because again the test showed that compound A gives positive tolling reagent, so we should have an aldehyde. Okay. Well, another way of connection, C double bond O, C double bond O, get them together, double bond. This should carry hydrogen, and this should be an aldehyde. Okay. Here we have double bond. This carbon should carry hydrogen. Looking for the first proposed structure for A, okay, we have isoprene, but here we don't have isoprene. So this structure is not acceptable. For this one, here we have isoprene and have isoprene. We have head to tail connection. So the upper one is not following isoprene rule, but the second proposed structure is. So the correct A structure will be this one. Citral unpiling with aqueous potassium carbonate yielded 6-methyl hept 5-ene-2-one and acetaldehyde. The formation of these can only be explained on the basis of the proposed structure. Propose a mechanism for their formation. So we have, this is the citral with potassium carbonate in water, give this species plus acetaldehyde. Well, which means that something is happening to this area. All right. If we recall aldol condensation, if we have an aldehyde or ketone with alpha hydrogen in basic condition, form anion enolate, the anion will attack another species, carbonyl, to form the anion. O has a minus, proton transfer, then dehydration to form alpha beta unsaturated carbonyl. Well, if we look for the species here, that's alpha beta unsaturated carbonyl, and the condition is basic. So this could be coming from this, and this comes from that, and to form this, that will be anion in here and carbonyl in here. So this is the one, this part, and that will be acetaldehyde, and the rest will be the carbonyl. So here we'll have this carbonyl, and here CH3, and the mechanism will be the other way around. See you next lecture.